AP Calculus BC, Unit 9, Day 1 lesson. So we're going to continue our conversation about series. We're going to start to focus on a bunch of different kinds of series and how to decide if they converge or diverge. So let's just talk about that idea on its own. So converging and diverging is a term that we've already used in calculus, generally talking about when things go to limits. Do they go to a certain value? Do they blow up and go to infinity or negative infinity? So this goes to 0. So it approaches, but it doesn't actually equal that value. It just gets ever closer to it. It converges. So that's what we say. It converges to 0. Whereas a very similar looking one, but if x goes to 0, 1 over 0 goes to infinity, which is unbounded. We say it diverges, okay? And technically, it's not okay to write that the answer is infinity because it's not really a quantifiable thing. So you would actually say diverges here if you're doing it technically. Now, we've been dealing with a lot of number series. A number series is a series that does not have variables in it like x. And so that's what we kind of started off with. And so here's a number series. It's a geometric series, right? It has an R value of negative 1/3. It has an A value of 2/3. And it equals the sum of the series is A over 1 minus R as long as the R value is less than 1 in absolute value. So the A value is 2/3, the first term, over 1 minus R. R is negative 1/3. Make sure you capture the negative. So it's going to be 2/3 over 4/3. So it's going to be 2/3 times 3/4. And it gives you 1/2. Okay. Now, this one right here is another geometric series, which is what we've had the most experience with. R equals just positive 1/3 this time. Now, last one, we call that an alternating series because it goes from positive, negative, positive, negative. The A value is 2/3, so this one's very similar to the last one. But, the positive and the negatives are kind of working against each other. So we're going to get a different value. It's going to go to a different value. Here, everything's positive, so you can imagine it's going to go to a bigger total sum, right? And in fact, it is double the sum of the other alternating version. Now, just to draw a picture for you, these two are behaving kind of in different ways. This one, it's like the first, it's going all the way to 1 and from 0 to 1. And so the first chunk is 2/3. So that's this. So on the first partial sum, we're all the way over here to 2/3. And then 2/9 would be, well, this is a third. So if you divide this into 3, then that's the next partial sum, the next one, and the next one, and the next one, next one, next one, next one. And it approaches, this total sum approaches this like wall. Okay? I'll kind of say it's like the wall. This one's a little different. This one, it's starting over here, if you say, okay, we're going to go 0 to 1, we already know it's going to go to 1/2, but the first partial sum is over here at 2/3. And then the second partial sum, we're going to subtract 2/9 from it. So it's going to end up almost back to 1/3. And it goes like this. And each partial sum we add, it gets closer and closer and closer. So alternating series, if they converge, do this kind of thing. They go back and forth past the number they could converge to. This one is just gradually approaching the final value. Okay. Now power series, these are series that have variables in the sense that they have x's. Okay. Sometimes we see variables like n or k or a. Those are just, r. That's not what we're talking about. But they have variables x in them. That's what makes a power series a power series. They have x to powers. Number series doesn't have any x's. A number series is pure numbers. Okay, a power series, we're going to actually plug a value of x at some point to evaluate it at that value of x. So this is going to work for a bunch of different values of x. This is sort of the general, just kind of a generic look at it. They look like polynomials. We have Taylor and Maclaurin series. They're built off calculus derivatives at a single point, which we call the center, or the a value. Our goal is to create a truncated Taylor series that are closely matching well-known functions. So it's not reasonable to take all infinite terms to get the exact answer. So we're going to truncate it, take as many terms as we need to get the accuracy that we desire. And we've done that already last unit, Lagrange error bound. So here's the sine series. If you take all of them, it converges to sine x. Now, by the way, this converges for all x, okay? So negative infinity to positive infinity is the interval of convergence, okay? Just a simple note, you need n equals 31 terms to produce an answer that is 10 decimal accurate for this one. So if you take 31 terms, you'll get 10 decimal places of accuracy, which is maybe more than you need. Here's another one. This one doesn't converge for all x. It converges from -1 to 1. Okay, so we've seen some of these before. We're going to explore other number and power series. Okay, so these are the ones we've seen so far, but we're gonna see some other new ones that we haven't really dealt with, and we're gonna ask ourselves a few questions. Do they converge? If it's a number series, what do they converge to? And that's going to be more specifically geometric series. That's what we know. That's the only one that I've introduced to you and that you need to know. The formula that we used up there, S equals A over 1 minus R. If it's power series, converge on what intervals? We want to find the interval of convergence and we've done that a bit with geometric series, but we're going to learn how to do it in general for any series. Something associated with the interval of convergence called the radius of convergence, and it's really half the distance between one edge to the other edge of the interval of convergence. And usually the interval of convergence is right around the center that we used, to create a power series or whatever. So here's some examples. We have a number series. This is not geometric, okay? If I plug 1 in, I get 1 over 3 for the first term. I plug n equals 2 in, I get 2 over 5. If I plug 3 in, I get 3 over 7. Plug 4 in, I get 4 over 9. And it keeps going. Now, does the series converge? The sequence seems to be going closer and closer to like 1/2. It seems like the terms approach converge to 1/2. The individual terms, the sequence. But as a series, we got to add them all up. So if we add them all up, by the way, this is actually something we're going to be doing a lot. We could take the limit of the terms and see what happens then, because based off that, we can kind of get some quick answers sometimes. They go to, if n goes to infinity, these are the dominant terms, right? L'Hopital's rule, infinity over infinity. And you can take derivative the top and bottom and reevaluate, or just, do in your head. It goes to 1/2, right? The series goes to 1/2. But when we sum them, when we add them all up, they actually blow up. They go to infinity. Okay. And and I think this should make sense. The individual terms here are actually getting bigger every time they're getting bigger. So I feel like it makes sense that if we add them all up to an infinite amount of them, it would just blow up. It's always getting bigger. So the terms have to get smaller, and it's not even just get smaller. They have to go to 0 to even have a shot at converging. Okay, so that sets up one of our tests. We're going to learn a bunch of different tests. Some apply to all kinds of different series. Some apply to certain specific series. This is called the nth term test. It's a test for divergence. Okay, it's not a test for convergence. This just possibly confirms if it diverges or not. Okay, a series will diverge if the limit of its terms do not approach zero. Okay. Now, it's a quick test. It's usually an easy test, even something you could do in your head just to rule out real quick, because if they don't go to zero, you shouldn't try anything else that's more complicated, because all of our other tests are going to be much more complicated. So if it doesn't go to zero, it diverges. If it does go to zero, that doesn't guarantee that it's going to converge. It doesn't guarantee convergence. Okay, so that's why it's a test for divergence. Doesn't guarantee convergence, but has to be true if it will converge. Okay, so this is at least one condition that has to be met, but it's not necessarily enough on its own. Just some examples. Uh, Here's another series: n equals 1 to infinity over 1 over n. If you were to take the limit as n goes to infinity of 1 over n, the terms do go to 0. Okay, but this specific series, still diverges, still blows up, still goes to infinity. Okay, so just throwing an example out there of one that meets that but still isn't good enough. So if it meets this, that's not enough to say converges. We're gonna have to do something else. But if this doesn't happen, then you're done. It diverges for sure. Okay. Now power series. So those are just some examples of number series. For power series, there's possible outcomes. There's a bunch of different possibilities. It can never converge and just always diverge, and just diverges for sure. Okay. It can converge at a single point. Okay. And that single point is usually at the center. Okay. And diverges elsewhere. It could converge on an interval, which is the most likely thing, that it's going to converge over an interval of values. And we've already been finding intervals of convergence for power series. It could be open or closed, meaning the edges could be included or not, and one edge could be and not the other. And we'll talk more about this later, about how to decide that. Okay. We've already had some experience finding intervals of convergence. The radius and the center of convergence are also terms that we associate with the interval of convergence that you might be asked to find. The extreme possibility is that it converges for all real values. And we've already seen a handful of series that do that. Sine, cosine, e to the x that we've been using, those power series, converge for any value of x that you plug in. They're not limited to a certain window. Okay, so that's sort of a summary of what we're going to be looking at this unit. This is really what we're looking for. The number series either converges or diverges. It's not one or the other partly, because it's just at a certain value, whereas a power series has values of x. So depending on what x value you use, it will converge or diverge, right? And that's where the interval of convergence comes from. So let's get into how do we figure out this interval of convergence. Now, we did this really simple thing, basic thing last unit with geometric series, but we have to apply this to any series. So there's this idea called the ratio test. It says if in a convergent series, the size of the next term has to be smaller than the previous one, which is something I already talked about. They have to be getting smaller, and that's not even enough. They got to go to 0, but they have to be getting smaller. Okay, so a sub n plus 1 is the next term, and a sub n is the previous term. Okay, the n values are counting the terms. So and it's just the absolute value. It can be positive, negative. So we put absolute values around it. So the next term better be smaller than the previous term. This always has to be true. Now, what we could do is we could do a little bit of simple math here. We could divide by the absolute value of a sub n on both sides, and then we get 1. We can combine them in a single absolute value. A sub n plus 1 over a sub n has to be less than what would be left over here, 1. Okay? Now check this out. This is how we found the R value. This is the R value if it is a geometric series. Okay? So this totally is consistent with what we were using on geometric series. The R value, which you can find by taking any term divided by the previous term, because it's a common multiple, has to be less than 1. That's what we've been doing. So this totally fits in with what we're doing, but now we're going to apply it to some problems that don't have R values, but we're still going to use the same idea. Now, for a series, there's a little typo here, it should be a plus. The limit as n goes to infinity equals some value, okay? L for limit, okay? Now, depending on what this value is going to tell us if it converges. If it's less than 1 all the time, then it converges, right? If it's less than 1. If it is greater than 1, then it diverges. If it is equal to 1, it's inconclusive. It's like indeterminate. Like we can't really say it might converge, it might diverge. Okay? So I have to figure out other ways. And those are the edges. Those are whether it's going to be open or closed interval of convergence. So, all right. Now let's do a couple of examples. Okay. Now this doesn't tell you if the series will converge, just what it'll converge to. It's not going to give you the sum. Okay, we're not going to be able to find the sum. This tells you, this is helping you decide if it will converge or not. Okay, and where. So here's some examples of number series. Does it converge, diverge, or is it inconclusive? Okay, so we're not finding interval of convergence. Okay, power series, you find interval of convergence. So we could just write some numbers out and just see what's happening. If you plug 1 in, you get 3 over 6. If you plug 2 in, you get 9 over 26. If you plug 3 in, you get 27 over 126, and so on. Are the terms getting smaller? That was 1/2. That's almost 1/3. That's almost 1/5. Yeah, the numbers are getting smaller. It looks like they're going to 0. And so, we could do the nth term test. In my head, I would say, yeah, if we take this to infinity, it's going to go to 3/5, which is no. It's okay. Sorry. Nth term test. Limit as n goes to infinity of the of 3 to the n over 5n plus 1. So you take it of just the term. Don't have the epsilon in it. And this is going to be infinity over infinity. These are the dominant terms. This one dominates that one. This one's grown way bigger. And so it does go to 0. Now, that doesn't tell you if it converges. And that's something you can just do in your head. If it does go to something other than 0, then you want to officially write it down as your work. Okay? But we're going to use this thing up here called the ratio test. So this is inconclusive. It might be good to just write it down just to get the hang of it. It's pretty simple. So the ratio test, we're going to take the limit as n goes to infinity. This is stuff you have to write in your work. The absolute value of the 3n plus 1 term, so you plug in n plus 1 wherever there's an n, divided by, okay, now, if you have a fraction and then you divide it by another fraction, we can just multiply by the reciprocal. And I'm going to jump to that result right away here. So I'm dividing by the previous term, which is the same thing as multiplying by its reciprocal. It's just going to be a lot less messy. You're going to want to get to that eventually, so might as well just start with that. So this is the next term divided by the previous term. Now, if we take the limit as n goes to infinity of this, it's going to be infinity over infinity, right? But we can look at, and we could, usually I'm not going to write this, okay? This is not what you need to show. I'm fine with you taking some shortcuts here, but really what you want to do is kind of look at those two together. It's infinity over infinity. So then we take the limit as n goes to infinity. You could do L'Hopital's rule, and L'Hopital's rule L'Hopital's rule would say, okay, take the derivative of the top. The derivative of the top would be 5 to the n times the natural log of the base. The derivative of the bottom would be 5 to n plus 1 times natural log of the base. These would, and the derivatives of these would be 0. These would reduce with each other. And now, if you just write it in, you get 1/5, right? Just get 1/5. And so we could do that with these terms also. So what I would do is I'd say, okay, well, I know these terms are going to become negligible, right? Just a random plus 1 compared to infinity. Like those are negligible, okay? So I'm just focused, like this one right here, I could, use rules of exponents and say, oh, well, that's going to be 3 to the first power, right? And then these two, that's going to be 5 to the first power. And so I know that I'm going to get 3/5. And then I needed to then decide, well, is that less than 1? It is less than 1, right? So it converges. Okay, so I'm going to be okay with you guys being a little lazy with the work and stuff, not having to show L'Hopital's rule and, but I'm expecting to see some like work on your paper that kind of shows me that you're doing it. Okay, this one, we could try the nth term test just to, get practice with it. It's a new thing. It rarely gives you a conclusive answer, but when it does, it's worth it. So if we take the limit of this, now this is going to infinity over infinity, but factorials way blow away exponentials. So it is going to 0, but that is inconclusive. That doesn't tell you, okay? So we're going to jump to the ratio test. Now, when you're doing your homework, I want you to write the name of the test you're using. Every time, show the work very officially. Okay, so the official work of the ratio test, limit as n goes to infinity, absolute value of the next term divided by the previous term, or multiplied by its reciprocal. Okay, so just set it up. Now, if you can, let's reduce things, okay? Before we even try and take the limits, like rules of exponents, you'd subtract this from that, and you would get a 2 on the top. Factorial is n plus 1 factorial is n plus 1 times n factorial. So then we could cancel the n factorials out, and this is what we have. So I haven't done any limits yet. I just simplified it, like straight out simplified it. I didn't even get rid of any terms. Now, if I take the limit of this, it goes to 0, which is less than 1, which means it converges. Okay? If you get 1, then that's inconclusive, and you might have to use some other tricks. Now, for a power series, we're asking the same questions, but we're asking where does it converge, diverge? Where? So we're trying to get an interval of convergence. Now we're going to use the same setup. Now you could try the nth term test to see if it converges no matter what everywhere. It's unlikely to, or if it diverges everywhere. So if you do this, you get infinity over infinity. The x is just a number, okay? It could be any number. I would say that oh man, I don't know. These are the dominant terms. So this is kind of iffy. I don't even know if we can really use it right now because it depends on the value of x, right? Depending on the value of x, if x is smaller than 10, then the bottom is going to dominate. It's going to go to 0. So that's not even going to be helpful. So with power series, we really actually should just go directly to the ratio test. The nth term test isn't going to help us, okay, for a power series that has x's in it. So the ratio test, we're going to take the limit as n goes to infinity of the next term. Now make sure you add any parentheses that need to be added. I don't really need the parentheses on the exponent, but I do need parentheses on that n, divided by the previous term or multiplied by its reciprocal. So you want to show this, write this, absolute values are required, the limit's required. I'll take off points on your test if you don't have this stuff. Now let's just use simplification thing. So we have these guys. I could use rules of exponents and just say there's a 10, right? And then we have these guys. When you use rules of exponents, I just have an x. So I'm going to rewrite it n plus 1 over n times x over 10. Now, remember, we're taking it n goes to infinity, not this guy. This is just a number. It just hangs out here. But this is the part that's going to be infinity over infinity. But those are the dominant terms. It's going to go to 1. And so we're going to get the absolute value of x over 10. Once we take the limit, that's the result, okay? So this is how power series are going to work. Usually you're going to get an absolute value with x's in it after the n's go away and you've taken the limit. Now, this is the thing that needs to be less than 1, okay? So we need to solve this absolute value inequality, however you want to do it. I mean, we've looked at lots of different ways. You could say, okay, well, it's going to be between -1 and 1, right? And then you can multiply both sides by 10. Okay? Or you could multiply both sides by 10 first before you get rid of the absolute value. Okay? Now, or you could use the rule of posse and say, well, this is 0. We're going to go 10 away on both sides. And these are going to be open dots. Okay? So your final answer, the interval. Now, here's the question, though. And I told you before, when it equals 1, it's inconclusive. It could converge. It might diverge. And so right now, these open dots are assuming we're not even looking at that. So let me start to show you how we deal with the edges, the endpoints. So what about the endpoints? Positive 10 and negative 10. Okay? This is what we do. So if we plug in x equals 10 into the original series, the original power series, we get a number series. Get a number series out of it. Okay, and that number series, so you would actually, this is the work you'd show, you'd rewrite it, n equals 0 to 8, and you plug x equals 10 in here. And then you could simplify it. And these guys would actually cancel, and it'd be this. And the series would be 0 plus 1 plus 2 plus 3 plus 4. Clearly going to diverge because you would then, to prove this, you would take the limit. You would do the nth term test. You'd write down what test you're doing. You do nth term test. Limit as so you would say limit as n goes to infinity of the nth term goes to infinity, which doesn't equal 0. I mean, that's the key thing. It doesn't equal 0, but it's obviously, so it diverges. So that endpoint doesn't work, right? And then you'd have to do it for the other one, x equals -10, because sometimes one will converge and one will diverge. So you plug in negative, because a lot of times what happens is that one will set up an alternating series. And a secret I have is that, so this one, they don't just totally cancel out. There's a negative 1 to the n times n. So the series is going to be 0, minus 1, plus 2, minus 3, plus 4. But it's still going to, the limit as n goes to infinity of negative 1 to the n is still going to blow up to positive negative infinity, which is not 0, so it diverges. But sometimes alternating series will converge easier than non-alternating series. So our answer, the interval of convergence, is negative 10 to 10. So we usually write that as an interval answer. Okay. The radius of convergence is, now the radius of convergence is this distance right here. It's half the distance from one side to the other side. It's the distance from the center to the edges. So it kind of makes sense that they call it the radius of convergence. The radius of convergence is 10, and it doesn't care about the endpoints or not. You just say the radius of convergence is 10, whether you include the endpoints or not. But you do need to check the endpoints, and they're each going to create their own number series when you plug them in, and you have to analyze them on their own like you would any number series. So this is the kind of work that we're going to be doing. This is today's assignment. And just try this out. We're going to be doing this ratio test a ton, and it's kind of a predictable thing. It involves limits and solving absolute value inequalities, but it's kind of straightforward. You just got to get used to setting it up and not making mistakes and being good at your limits and stuff. Okay, that's it.